Okay, chemists, today we're going to go over what's called reaction diagrams. So this will be your intro to reaction diagrams. So this is going to follow the course of a reaction. So you might have time written on the x-axis or some other variable that indicates this is as the reaction goes along. So let's pick this apart right here. Is the potential energy of the reactants before the reaction even starts. Usually going to be measured in joules or kilojoules. Over here, the distance from 0 joules or kilojoules up till the energy of the products is the measure of the potential energy of the product. So this is E right here, is the amount of energy you'll have after the reaction is complete. So here's how we read this. This is the potential energy of the reactants here. This is the energy that I need to add in order to get the reaction to go on its own. This right here is what we call the reaction coordinate, or the activated complex, or the transition state. There's 3 different ways we can describe this point up here. So therefore B, which is the distance between the energy of the reactants and the energy of the activated complex, is called the activation energy for the forward reaction. Now, if this was a reversible reaction, it can go in both directions. So the activation energy for the reverse reaction is the difference between the potential energy of the products and the potential energy of the transition state or activated complex. So therefore, this is the distance that is measured, would be the activation energy for the reverse reaction. Now, the change in energy for the entire reaction is the difference between the potential energy of the reactants before the reaction starts and the potential energy of the products. So F here is the difference between the start and the finish, and that's called the change in energy for the reaction, or delta E. So let's pick this apart one more time again and see if we understand each of the letters. This right here, A, is the potential energy of the reactants. And then the reaction starts, and I need to add a certain amount of energy. So this is the potential energy of the reactants. I need to add a certain amount of energy to get the reaction to go on its own. This is called the activation energy of the forward reaction. And this here is the energy, C right here is the energy of the transition state. So that's the highest energy position that this reaction will have. And that's C right here. Then after the reaction is at its maximum energy, at some point in time, it will progress on its own. And right here, E is going to be the potential energy of the products. F is the toughest one to understand. That's the difference between the reactants and the products, and that's going to be the delta E for the whole reaction. That would be F there. Now, how we decide whether this is an endothermic or exothermic reaction is to analyze the beginning or the end and the end. So this is the amount of energy of the reactants, and this is the amount of energy of the products. Because the products have more energy than the reactants, that means that the system must have gained energy or absorbed energy. Therefore, this particular reaction is going to be endothermic, and my delta H will be a positive value. I'll show you real quick what a graph would look like if it was exothermic. If it was exothermic, it would look like this, where the potential energy of the products would be less than that of the reactants. So this would have a negative enthalpy change or energy change, indicating it is an exothermic reaction. So those are the different parts of the reaction diagram. Okay, the last thing that we want to talk about is a catalyst. You might have heard of a catalyst in that it speeds up a reaction. Enzymes are an example of like biological catalysts. So when you add a catalyst, it actually changes the reaction mechanism. So it changes the reaction coordinate or transition state to a lower energy transition state. So if I were to add a catalyst in here, what's going to happen is that the activation energy is going to decrease like such. So that's how it speeds up a reaction. It causes a reaction to require less energy. So it changes the activation energy of the forward and reverse reaction the same way. That means that both the energy of the forward reaction activation energy, the reverse reaction activation energy, and the energy of the transition state will be different. That's how a catalyst affects a chemical reaction.